as promised, a quick introduction to Newton's third law, which we are going to look at next in AP Physics C. We'll talk a bit more about this in class on Monday. The big idea here is for every action, there is an equal and opposite reaction, right? That's Newton's third law as usually stated. And we want to be able to use this so that we can identify action-reaction pairs of forces and then do interesting things with them. So kind of a fun scenario. A starship captain beams down onto a frozen, frictionless pond. Communicator is dead. How can he escape the pond to complete his mission? He has no idea. So there's a hint. This is at the beginning of our Newton's third law video. So there's going to be an answer in Newton's third law. But let's talk about Newton's third law, and we'll come back to this. The third law, even though it's stated there's an action-reaction pair or there's an equal and opposite reaction, what does that mean? Well, that means that when you have a force, there is always a reaction force that is equal in magnitude, the same amount of force, same number of newtons, opposite in direction. So if one is to the left, the other is to the right, up, down, this kind of thing. And simultaneous, they're acting at the same time. It's not a delayed reaction of like you push something and later it pushes back. It happens at the same time. They're the same kind of force, so they're either both tensions or both forces of gravity or both electromagnetic or something like that. And then they are acting on two different objects. And this is probably the most important piece to separate this from Newton's first and second law. In the first and second law, all we cared about was a single object, one, and the forces acting on it. In the third law, we're talking about interactions between multiple objects. So the third law mantra, if we were all sitting in class together, I'd probably make half of you say, A pushes on B pushes on A pushes on B pushes on A, right? Doesn't matter what it is, C pulls on D pulls on C, and so on and so forth, right? It doesn't matter what the initial force, the action force is, there's always a reaction. And the way to do it is just to flip it around. C pulls on D pulls on C. A pushes on B pushes on A, right? So if we're going to talk about the action-reaction pair, we can look at some examples, right? A teacher pushes on the wall. What's the reaction pair? The wall pushes on the teacher. So Isaac Newton likes that one, right? Action-reaction pairs involving this block, right? If we're talking about gravity, the Earth pulls on the block pulls up on the Earth. The normal force, the ramp pushes on the block, and the block pushes on the ramp, right? It does not matter what kind of force it is, it follows this same exact format. So if we go back to our stranded captain on the frozen frictionless pond with the dead communicator, what if he were to throw his communicator, which is useless to him as a communication device, but could be useful because it's a mass. If he throws it, he will apply a force, the force that the captain applies to the communicator. And in reaction, the communicator will apply an equal and opposite force on the captain. Probably won't be a very big force because it's a small device and, you know, doesn't take much force to get it to go flying. But if it's a frozen frictionless pond, that could be enough for him to escape. So why do we need the third law? Well, obviously we can think about fun scenarios like the captain on a frozen frictionless pond. But if we're only talking about a single object, then no, we don't need it. The third law doesn't actually help us. It helps us understand the interaction between two objects. And we need it to solve what we call two-body problems, which we will talk about kind of as our next big thing. So another scenario to consider, and this kind of links the idea of Newton's first, second, and third laws. If you imagine two carts pushed together, and they can push each other apart via some means, a spring, a small explosion, whatever it is. If you played around with the carts that we have, they have a little plunger in them that can explode out. And I'll do a demo of this when we get together in class again. But what's the same? Well, according to Newton's third law, they each apply an equal and opposite force. They each apply the same amount of force to each other. But if one of them is more massive than the other, having the same net force will result in a different acceleration. A low mass thing will have a big acceleration, and a high mass thing will have a small acceleration. And this, that connection between the interaction force, equal and opposite forces, and Newton's second law where accelerations can occur, ends up being kind of the big deal. So that's the end of this piece. You can read more about this, and we'll talk more about it in class.